Hello, and welcome to my Lab 2 presentation on combustion dynamics in a RICA tube. The motivation for this Lab 2 was to be introduced to measuring periodic fluctuation properties and acoustic oscillations using a RICA tube, which is an open-ended pipe with an internal compact heat source. Our main goal was to create resonance inside of the pipe. By heating the tube at 1/4 of its length from the bottom, combustion intensity and the heat release rate will fluctuate with time. These fluctuations cause pressure and acoustic oscillations within the tube, which in turn reinforce the heat release fluctuations, creating a cycle. Sound generated by the tube comes from a standing wave whose wavelength is almost twice the length of the tube. In this case, the tube is 6 feet, so the wavelength is 12 feet. In the Engineering, Science, and Mechanics Building Room G2, we set up our experiment. The instrumentation used for this experiment was a RICA tube, a piezoelectric pressure transducer, which was used to monitor acoustic pressure fluctuations, a photomultiplier tube, which was used to measure radiation emitted by the flame, and a rotimeter, which was used to measure fluid flow rates. For this setup, 3 piezoelectric pressure transducers were placed at 18-inch intervals along the tube, and 1 photomultiplier was used. Our goal was to measure the RMS voltage, frequencies, and phase angles of the different positions of a burner. We did this by first measuring these values at the 0-inch location with the valve closed and then with the valve opened. We closed the valve and then raised the flame to 2 inches and then again to 6 inches, recording the same data at both locations. These positions are relative to where the burner is started from, which is at the bottom of the window shown in the picture. By first calculating the speed of sound, an estimate for the resonance frequency could be made using the calculation shown. This value is around 93 Hz. In order to calculate the sound pressure level in decibels, the pressure transducer table was used to find a value for the PRMS, which is the root mean squared fluctuation of the pressure field. PRMS was found by finding the slope of the line to be 97.4 and dividing the voltage, which was converted to millivolts, by the slope. The sound pressure level could then be calculated. Here are the results from the sound pressure calculations from the measurements taken by the 3 pressure transducers and the photomultiplier transducer. The pressure transducers were converted to decibels while the PMT values stayed in volts. The peak frequencies at each location was also recorded. The resonance frequency estimate was 93, which is close to the recorded 97 Hz. This data shows that for the measurements with the valve closed, as the height grows, the frequency decreased to 1, making it impossible to hear the sound. This proves that at the lower ends of the pipe, the combustor is pulsating, thus making a sound which we observed in the lab. We can also see that the frequency is 1 at 0 inches when the valve is opened. Buoyancy is produced by the combustion, which causes an upward draft in the tube for acoustic oscillations to occur. However, when there is an escape route for the heat other than the top and bottom of the tube, these acoustics will not happen. The relative phase angle for both the open and closed conditions at 0 inches were also calculated. This was done by taking the position of pressure transducer 2 as the base point and subtracting it from the other points. Supplemental question 1 asks if you can use a 415 to 450 nanometer filter instead. And yes, you can. There are intermediate species that form from the combustion that are visible through different filters. One of the species emitted when you burn propane is a carbon-hydrogen bond, and this is visible in the range of 415 to 430 nanometers. Question 2 asks if you can use this filter with hydrogen fuel instead of propane fuel. When you burn propane, oxygen is separated and carbon gets bonded to the hydrogen. If you just burn hydrogen, however, no carbon is produced, thus not giving you the carbon-hydrogen bond that is visible through that lens. The last question asks how to make a tube that is tunable. The frequency at which the acoustic oscillations occur is directly related to the speed of sound, which is directly related to the temperature of the gas. Thus, to make a tunable tube, you need to be able to vary the temperature at which the gas is at. In conclusion, by using an open-ended tube and heating it 1/4 length from the bottom, we can generate sound waves audible to the ear. This occurs because of the cycle of heat release, which causes velocity and acoustic oscillations to occur, which in turn reinforce more heat fluctuations. From the data and observations in the lab, we learned that as frequency decreases, so does the audio. We also observed that when there is an escape route for the heat, such as an open valve, acoustic oscillations will not occur. Thank you.